7, we're going to be exploring Pascal's Triangle and the expansion of x plus y all to the power of n. Now the first example says we have to write the following in simplest form. We have x plus y to the power of 0 equals, anything to the power of 0 is equal to 1. Then we'll expand x plus y all to the power of 1. Well, that's just simply x plus y. On part B, let's expand x plus y to the power of 2. So to make things easier, I'm going to write in as a set of two binomials, and then we can FOIL that out. When we do so, we get x squared plus 2xy plus y squared. Now let's expand x plus y to the power of 3. X plus y to the power of 3 expanded looks like x plus y times x plus y times x plus y. Well, from the first set, we've already expanded x plus y times x plus y. So let's write that out, times x plus y. So we have x plus y times x squared plus 2xy plus y squared. Now we have to distribute every term in the first binomial by every term in the trinomial. When I distribute the x through each term in the trinomial, I get x cubed plus 2x squared y plus xy squared. Now I'll distribute each of the y into each term of the trinomial. So I get x squared y 2xy squared, and lastly y times y squared is y cubed. So from there, going in decreasing order of the x coordinates and increasing order of the y exponents, I get x cubed plus, here I have 2x squared y and 1x squared y, so 3x squared y, plus I have xy squared plus 2xy squared, so that's 3xy squared, plus y cubed. So going on to part C, complete the following using your answers above. So for x plus y to the power of 0, that equals 1. X plus y to the power of 1, that equals x plus y. X plus y squared equals x squared plus 2xy plus y squared. X cubed, we got x cubed plus 3x squared y plus 3xy squared plus y cubed. And we didn't do the expansion for x plus y to the power of 4, but you would get x to the power of 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. So let's just explore what's happening with the expansions with exponents 0 to 4. State the number of terms in the expansion of x plus y squared. So if we look at that expansion, we have 1, 2, 3 terms. If we look at the expansion of x plus y cubed, we have 1, 2, 3, 4 terms. If we look at the expansion of x plus y to the power of 4, we have 1, 2, 3, 4, 5 terms. So what we're seeing is we have one more than the number on the exponent for the number of terms. So for x plus y to the power of 20, we would have n plus 1 terms. So we would have 21 terms. Now let's look at the sum of the exponents in each term of the expansion of x plus y squared. Well, if we look back here, the sum of the exponents is 2. Okay, now if we add up the exponents here, we have 1 plus 1, the sum is 2. And y squared, the exponents is 2 again. So the sum of the exponents in each term for x plus y squared is 2. For x plus y cubed, notice that the sum of each of the exponents equals 3. So x cubed, x squared plus y to the power of 1, 2 plus 1 is 3. Okay, 1 plus 2 is 3. And we have lastly an exponent 3. So all of the exponents for each term will add up to 3. Okay, same thing for x plus y to the power of 4. The exponents add up to 4, add up to 4, add up to 4, add up to 4, and add up to 4. So if we were to go to a further expansion, x plus y all to the power of 20, we would have a sum of 20 in the exponents. So now let's just look simply at the coefficients. So for x plus y to the power of 0, we have a coefficient of 1, or a constant in this case. X plus y to the power of 1, we have coefficients 1 and 1. For x plus y to the power of 2, we have coefficients 1, 2, and 1, right here. For x plus y to the power of 3, we have 1, 3, 3, and 1. Okay, for the expansion of x plus y to the power of 4, the coefficients are 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. So if we were to set this up in a triangle now, we would get 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, now basically what we're creating is Pascal's triangle. And what we're noticing is that there's a pattern from row to row. Okay, all of the numbers on the outside of the triangle will always be 1. Let's go from row 2 to row 3. How do we find this middle number? Well, we add 1 plus 1 is 2. We've created a little triangle here. Okay, let's go from row 3 to row 4. 1 plus 2 is 3, so this triangle adds to 3. Okay, 2 plus 1 is 3, so this triangle adds to 3. Let's go from row 4 to 5. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And again, all of the numbers on the outside of the triangle will always be 1. So if we had to add another row, say for the expansion of x plus y to the power of 5, just looking at the coefficients, we'd have 1's on the outside, and then we just add the numbers above to make a triangle for the sum below. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So the coefficients, if we were to expand x plus y to the power of 5, would be 1, 5, 10, 10, 5, and 1. If you just flip to the next page now, properties of the expansion x plus y to the power of n, we get the following. And as you can see, looking at the coefficients from the previous page, we did in fact have 1, 5, 10, 10, 5, and 1. One thing you'll notice about the exponents, as we move from x to the right, okay, the x exponents go down. So we have 5, x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, and x to the power of 0. Whereas the exponents on the y values increase. Y to the power of 0, y to the power of 1, y to the power of 2, y to the power of 3, y to the power of 4, y to the power of 5. So figuring out how many terms there are for each row, let's just take a look. So if n is 0, we have 1 term. If n is 1, we had 2 terms. If n is 2, we had 3 terms. If n is 3, we had 4 terms. So what we're seeing is that there are always n plus 1 terms. The sum of the exponents of x and y in each term will always be equal to n. So for example, if we look at x plus y to the power of 3, each term adds to it the exponent of 3. So 3, 2 plus 1 is 3, 1 plus 2 is 3, and 3. So the sum of the exponents of x and y in each term will always be n. Note that the exponents of x decrease term by term from n to 0. So just like I stated here, we have x to the power of 5, x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0. Whereas the exponents of y will increase, okay, going from 0 all the way up to n. The coefficients, as we noticed from Pascal's triangle, form a symmetrical arrangement. Okay, I'll just show you back here. We had 1, 5, 10, 10, 5, 1. It's symmetrical. Okay, 1, 4, 6, 4, 1. Also symmetrical. 1, 3, 3, 1 is symmetrical. So now let's investigate Pascal's triangle. The coefficients in the above expansion of x plus y to the power of n can be put in a triangle array known as Pascal's triangle. We're going to use these patterns to complete the next 3 rows. Okay, so again, the outside of the triangle will always be 1, and we just take the 2 terms above and create a little mini triangle. We add these numbers and put the sum of those numbers below. 1 plus 5 is 6. Create another triangle. 5 plus 10, 15. 10 plus 10 is 20. 10 plus 5, 15. 5 plus 1, 6, and the outside's 1. For the next row, 1 go on the outside, and we take the 2 terms from above and add them to get the number below. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7. And one more row. 1's on the outside. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35, 56. 35 plus 35 is 70. 35 plus 21 is 56. 21 plus 7 is 28. And 7 plus 1 is 8. So let's complete the following expansions without actually having to multiply x plus y times x plus y times x plus y times x plus y. Okay, we're going to start with the greatest exponent on x. And I'm just going to first write out the variables and then I'll fill in the coefficients after. So going in decreasing order for x's and increasing order for y's. We have x to the power of 5, y, plus x to the power of 4, y squared, plus x to the power of 3, y to the power of 3, plus x to the power of 2, y to the power of 4, plus x to the power of 1, y to the power of 5, plus x to the power of 0, and y to the power of 6. So let's just check out the coefficients for the expansion of x plus y to the power of 6. Okay, 1, 2, 3, 4, 5, 6. Remember, it's n plus 1 for the number of terms. Okay, so I have 1, 2, 3, 4, 5, 6, 7 terms. That means I have to use this row here. So my coefficients will be 1, 6, 15, 20, 15, 6, and 1. Let's try one more. X plus y to the power of 7. Okay, we know it's going to be x to the power of 7, and then we're decreasing in the exponents on the x coordinate. or the x value, and we're increasing in exponents on the y value. So add x to the power of 6, y to the power of 1. X to the power of 5, y to the power of 2. X to the power of 4, y to the power of 3. X to the power of 3, y to the power of 4. X to the power of 2, y to the power of 5. X times y to the power of 6, plus lastly y to the power of 7. Okay, so let's count out. There's 1, 2, 3, 4, 5, 6, 7, 8 terms. N plus 1 terms. Our n is 7, so that means we have 8 terms. So we have to go to the 8th row. 1, 2, 3, 4, 5, 6, 7, 8. We get 1, 2, 3, 4, 5, 6, 7, 8 terms. Perfect. Okay, so we have 1x7, 7x to the power of 6y, 21x to the power of 5y squared, 35x to the power of 4y cubed, 35x to the power of 3y to the power of 4, 21x squared y to the power of 5, 7x times y to the power of 6, and lastly 1y to the power of 7. For part C, which row of Pascal's triangle is equivalent to the coefficients of the terms in the expansion of x plus y to the power of 6? Well, you'll notice, I've already stated this, it's always going to be row n plus 1. So if we have n equals 6, that means we're looking at row 7. If we have n is 7, then we're looking at 7 plus 1, that will be row 8. Okay, if n is 12, we're looking at row 13. So flipping to the next page, we're now going to apply Pascal's triangles to combinations. So Pascal's triangle is actually an array of combinations. The reasoning behind this will be developed in the next lesson when we look at the binomial theorem. So let's compare Pascal's triangle in combination form. So notice row number 1, we have a coefficient of 1. That's just 0, choose 0. For row number 2, we have coefficients 1 and 1. Combinations, 1 choose 0, 1 choose 1. For row number 3, Pascal's triangle is 1, 2, 1. As a combination, we have 2 choose 0, that's our 1. 2 choose 1, that's our 2, and 2 choose 2, that's equal to 1. Okay, for row 4, we have coefficients 1, 3, 3, and 1. 3 choose 0 is our 1, 3 choose 1 is our 3, 3 choose 2 is our 3, and 3 choose 3 is equal to 1. So you'll notice for each of the rows, it's going up in the value of r. Okay, recall that we have n choose r at a time. Okay, so for example in row number 5 it would be 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. You stop once you've selected as many as you can. Okay, you can never take more than n elements. So state the first 3 terms of the 8th row of Pascal's triangle in numerical form. Okay, so for the 8th row, we would have 1, 7, 21, 35, 35, 21, 7, and 1. So the first 3 would be 1, 7, and 21. For combinations, we would have 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, and lastly 7 choose 7. So the first 3 are equivalent to 7 choose 0, 7 choose 1, 7 choose 2. 7 choose 0 is equal to 1. 7 choose 1 is equal to 7. and 7 choose 2 is equal to 21. Okay, we could also look at the last three terms of the 8th row. Okay, so that would be 21, 7, and 1. Okay, and the last three combinations would be 7 choose 5, 7 choose 6, and 7 choose 7. Let's take a look and see if we can apply our technique with Pascal's triangle for finding the next row and do the same in combination form. So let's use Pascal's triangle to write the following as single combination. So 4 choose 2 plus 4 choose 3, let's find that. We have 4 choose 2, 4 choose 3. If I were to create a little triangle here, I would add up to 5 choose 3. Okay, now let's try 6 choose 0 and 6 choose 1. Okay, if I were to create a triangle, I would get 7 choose 1. Okay, and lastly, the rule for this, if I have n choose r plus n choose r plus 1, that will add up to n plus 1 choose r plus 1. Okay, and let's look back at that. Okay, we had 6 as our n plus 1 is 7. Okay, so that's the number on the left side. And then let's look at what we're taking at a time. It will be r plus 1. Well, our r was 0. 0 plus 1 is 1. Okay, same thing here. Our r was 2. 2 plus 1 is 3. So let's investigate three sums equal to 2 to the power of n. Complete the table for the sum of the numbers in each of the first 6 rows of Pascal's triangle. So for row number 1, the sum of the numbers in the row, well, let's add it up. It's equal to 1. And as a power of 2, that would be 2 to the power of 0. For row number 2, we had 1 plus 1. So that's equal to 2. As a power of 2, 2 to the power of 1. For row number 3, we have 1 plus 2 plus 1. That equals 4. So we have 2 to the power of 2. Next up, row 4, we have 1 plus 3 plus 3 plus 1. That equals 8. As a power of 2, we get 2 to the power of 3. Row number 5, if we add that up, okay, 1 plus 4 plus 6 plus 4 plus 1, we get 16. And that gives us 2 to the power of 4. For row number 6, adding up 1 plus 5 plus 10 plus 10 plus 5 plus 1, we get 32. As a power, that's 2 to the power of 5. So what if we're looking at row n? As a power of 2, we get 2 to the power of n minus 1. Or, if we looked at n plus 1 as our row, it would just simply be 2 to the power of n. So look at row 5 in Pascal's triangle in combination form. The sum of the numbers in this row can be written as 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4. As a power of 2, we would write this as 2 to the power of 4. Okay, because we're writing it as 2 to the power of n. And just going back here, the sum of the number in the n plus 1th row of Pascal's triangle will always be 2 to the power of n, just as we saw here. And just a reminder, we had 1, 2, 3, 4, 5 terms. So this would be row number 5. Going back to row 5, we had 2 to the power of 4. Let's look at row 7 and complete the following. We have 1, 2, 3, 4, 5, 6, 7 terms. That's row 7. So if we're applying that to n plus 1, that means our n had to be the 6. And it's always going to be the n value on your combinations. Okay, so we get 2 to the power of 6. Okay, and you could simply calculate each one of these and it would add up to 2 to the power of 6, which is 64. Okay, and let's verify that. Let's look at row number 7 and we'll add up 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, and we do get 64. So to summarize, if we had a combination statement which is equal to the coefficients of the expansion x plus y to the power of n, we would get n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 all the way up to n choose n. That would be equal to 2 to the power of n. Okay, so the sum of all the combinations is always equal to 2 to the power of n, which is 1 less than the row number. Okay, just like we saw here, row number 6, 2 to the power of 5. Row number 5, 2 to the power of 4. It's always 1 less, or it's equal to the n value in your combinations. So let's consider the expansion of x plus y all to the power of n. So we've seen these expansions so far, to the power of 0, to the power of 1, 2, 3, 4, and 5. So the sum of the coefficients. For row number 1, the sum of the coefficients would be 1 plus 1. And my apologies, it's not row 1, it's when n is 1. So when n is 1, we had 1 plus 1, which is 2. We get 2 to the power of 1. Okay, in row number 2, we have 1 plus 2 plus 1, which is 4. So we get 2 to the power of 2. In row 3, when n is 3, and row 4, we get 1 plus 3 plus 3 plus 1 is 8, which is 2 to the power of 3. If we kept this up, we would see that we get 2 to the power of n. So if you're referring to what n is, it's always going to be 2 to the power of n. If you're referring to the row, just note that the row number, when it's n plus 1, you will always, again, get 2 to the power of n. Okay, if you're just simply looking at row number n, you would have 2 to the power of n minus 1. It's always 1 less than the row number. So the sum of the coefficients in the expansion of x plus y to the power of n is 2 to the power of n. The following statements summarize the previous investigative work. The sum of the numbers in the n plus 1th row of Pascal's triangle is 2 to the power of n. Okay, so n choose 0 all the way up to n choose n is equal to 2 to the power of n. The sum of the coefficients in the expansion of x plus y to the power of n is 2 to the power of n. So let's determine the sum of the numbers in the 10th row. Well, if we're in the 10th row, that means we have n is equal to 9. Okay, because when we're in row n plus 1, we get 2 to the power of n. So 2 to the power of 9 equals 512. Okay, I'll just go back here just to show you one more time. So here we had the row number, okay, and say our row number was 6, we had 2 to the power of 5. So if our row number is 10, that means we actually have 2 to the power of 9. It's always 1 less than the row number. Determine the sum of the coefficients in the expansion of m plus n to the power of 12. Now this one's a little bit different because they're telling us n is equal to 12. It's not looking at the row numbers, it's what n is. So our answer would simply be 2 to the power of 12. And when we calculate that, you get 4,096. For the following ones, okay, we're not looking at row number, we're looking at what n is. Here, n is 15. So we have 2 to the power of 15, that equals 32,768. Now let's take a look at the second example here. We have 6 choose 0, and it goes all the way up to 6 choose 5. So that means we're missing 6 choose 6. Whereas here we went from 15 choose 0 all the way up to 15 choose 15. So the sum of all these coefficients or combinations is 2 to the power of 15. But here we're missing 6 choose 6. So we have to calculate 2 to the power of 6 would be the entire set of combinations, and then subtract 6 choose 6. From there we get 64 minus 1, and our answer is 63. Lastly, we're going to explore roots and how to figure out the number of roots using Pascal's triangle. Okay, we've done this question before. Paul and Catherine are considering the following problem. Find the number of roots from A to B if the paths must always move closer to B. So as we explored, we had 5 factorial because we had 3 east and 2 south. So that would be like east, 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 south, south. So there's 5 possible options, okay, in any order. And then you'll notice that we had 3 east, they repeat, and 2 souths that repeat. So we have to divide by 3 factorial, 2 factorial. When we calculate that, you get 10 rows. Okay, but this answer can also be found using Pascal's triangle. Okay, let's just look at this first pathway first, okay, going from A to B. How do the following answers relate? F compared to C and D. Well, if we apply Pascal's triangle, C plus D equals F. H compared to E and F. Well, E plus F equals H. And now I compared to F and G. F plus G equals I. So keeping this in mind, we can create Pascal's triangle on the triangle to the right, or sorry, the pathway to the right. So Pascal's triangle always starts with 1, and its outside rows are always equal to 1. So we can just put 1s right the way down. Now we can add the 2 numbers above, and we get the sum below. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 1 equals 3. 3 plus 3 equals 6. 3 plus 1 equals 4. 6 plus 4 equals 10. And therefore we have 10 roots from A to B. Okay, so the answer is 10 roots. So we can use factorials and permutations, or we can use Pascal's triangle. So Pascal's triangle and roots. The exploration on the previous page can be used to illustrate how Pascal's triangle may be used to determine the number of roots in a diagram. Notice that the numbers on the diagram on the previous page are part of Pascal's triangle as shown in the overlays below. Okay, so as we can see, we're going 1s on the outside, and then we just take the numbers above to get the sum below. Okay, so 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, and so on and so on. We can also look at this as combinations. 0 choose 0, 1 choose 0, 2 choose 0, 3 choose 0, 4 choose 0, 5 choose 0. Anytime we're choosing 0, we will get 1s. Okay, and then if we look on the right hand side, okay, 0 choose 0, 1 choose 1, 2 choose 2, 3 choose 3, 4 choose 4, 5 choose 5. These all equal 1, just as we see in Pascal's triangle. Okay, when n is equal to 1, we have 1 choose 0, 1 choose 1. When n is equal to 2, we have 2 choose 0, 2 choose 1, 2 choose 2. Okay, when n is equal to 3, we go from 3 choose 0 all the way up to 3 choose 3, and so on, so on. So as shown in the second diagram, the answer 10 is equivalent to 5 choose 3, which we have here, which can be written in factorial notation as 5 factorial divided by 2 factorial, 3 factorial. Okay, and just a reminder that comes from n choose r, n factorial over n minus r factorial times r factorial. Okay, so we have 5 factorial on top. 5 minus 3 is 2 factorial. And then our r was 3, so 3 factorial. Okay, the supervisor of the city bus department is determining how many routes there are from the bus station to the concert hall. Okay, so from here to here. Determine the number of routes possible if the bus must always move closer to the concert hall. Let's first use Pascal's triangle. So we're going to start with 1 at the bus station, and moving to the right, those are going to be 1s, and then moving down, those are going to be 1s. So it's almost as if your paper is turned, and now we have Pascal triangle spreading out. Well, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 2 plus 1 is 3. 3 plus 1 is 4. 3 plus 3 is 6. 4 plus 6 is 10. 6 plus 4 is 10. 10 plus 10 is 20. 5 plus 10 is 15. 15 plus 20 is 35. So you should have 35 routes getting from the bus station to this corner. Okay, now similarly, there was 1 route from here to here, and there's 1 route from here to here. So if there's 35 routes here, there's also 35 routes here, and 35 routes to get to here. So we can just rewrite 35 and 35 to that corner, and 35 and 35 to that corner. And then we just carry on adding. 35 plus 35 is 70. 70 plus 35 is 105. 70 plus 35 is 105. And 105 plus 105 is 210 possible routes. Now, let's use permutations with repetitions. So let's just count how many ways we can move. So we have 1, 2, 3, 4, 5. 6, 1, 2, 3, and 1, 2, 3, 4. So there's 7 factorial. There's 7 possible directions on this first block here. Okay, so we have 3 east and 4 south. That gives me 7 factorial. We're going to divide by the repetitions. Well, there's 3 going east, and then the other repetition, 4 going south. So that's from the bus station to this corner here. Then we're going to multiply that by this bottom section. Okay, we have 2 east and 2 south. So there's 4 possible directions. Now let's divide by the repetitions. 2 east, 2 south. If we multiply, we get 35 times 6, and that also equals 210 routes. So there's one major difference between example 2 and 3. You'll notice here that these are 2 separate blocks, But in example 3, there's gaps in the box, right here and here. Okay, so I'm just going to let you know right away, we cannot use permutations because there are gaps in the rectangle, so that not all arrangements of 4 easts and 4 souths are possible. Okay, so for example, we can't go east, 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 east. That's not possible. And we can only use permutations when that is possible. Similarly, we can't go south, 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 south because there's this gap here. So since there are gaps, we cannot move. For example, south, 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 so south, 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 and then east, 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 east. That's not possible. So we can't use permutations because it's not one route. Okay, but we could use Pascal's triangle. So let's start by writing 1 on the top, and then as we move right, that's one root, one root, one root, and as we move south, we have one root, one root, one root, one root. Okay, and now we can just add up. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. 3 plus 1 is 4. 3 plus 3 is 6. 1 plus 3 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. Okay, and we had 4 on this corner, so we also will have 4 roots on that corner. 10 plus 4 is 14. 10 plus 10 is 20. 5 plus 10, 15. Same thing here. On this corner we had 15 roots. This will also be 15 roots. 15 plus 20 is 35. 20 plus 14, 34. 35 plus 34 is 69. 15 plus 35 is 50. 50 plus 69 is 119 roots. So just be very careful. If you have 2 separate blocks, you can use permutations or Pascal's triangle. And if you have gaps in your root, then you cannot use permutations. You have to use Pascal's triangle.